Hello everyone. So we were talking about relative motion. We discussed that rest and motion, these two are relative terms, right? It depends on the observer. For one observer you may be at rest, but for another observer you may be in motion. And things becomes a bit more tricky when your observer becomes dynamic, right? When observer itself comes into motion, things become a bit more dynamic, right? So let's say for example we can say that let's say that this is one train, right? This is one train which is moving in the right direction for now, and then there is another train on the another track which is also moving in the same direction. So these two trains are actually moving in the same direction, right? So if I talk about, let's say if v1 is the velocity of this train and v2 is the velocity of this train, so a person inside train 2 will not see train 1 with velocity v1. For a person inside train 2, the velocity of train 1 will be v1 minus v2, which is relative velocity of train 1 with respect to train 2. And for a person inside train 1, the velocity of train 2 is nothing but v2 minus v1, which is relative velocity of train 2 with respect to train 1. And how are we calculating these quantity? We know relative velocity of a body A with respect to body B is velocity of A minus velocity of B, right? Velocity of A minus velocity of B. And this V1 and V2 are the velocities which we are talking in the ground reference, right? With a stationary reference, the velocity of train 1 is V1 and velocity of train 2 is V2, right? Okay. To get a better clarity, let's solve one more problem on projectile motion, right? So the problem states that an elevator is descending with uniform acceleration and a coin is dropped which was at 6 feet from surface, and it comes to floor in 1 second. Calculate the acceleration of elevator, right? Elevator means you already know elevator is a lift, right? This is the elevator, right? And it says that it was coming down with the acceleration maybe a meter per second square. Let's assume that it was coming down with acceleration a meter per second square, right? So from the surface at let's say 6 feet height, from 6 feet height, a coin was dropped, right? A coin was dropped, and this coin reaches the surface in 1 second. So to cover 6 feet, this coin took 1 second, right? So let's note the quantities which we have. So initial velocity is 0 meter per second square, right? Distance this coin has to cover is 6 feet, and time it took is how much? It was 1 second, right? Now we need to find what? We need to find the acceleration of the elevator. So how this elevator is affecting the dropping of the coin? Think, if this elevator would have been in a stationary condition, this coin would have dropped with the acceleration due to gravity. There was nothing else into the picture, right? But since this elevator has an acceleration, we need to consider this acceleration and we need to think from the elevator point of view, right? Because the motion of coin is affected by its reference, which is elevator, right? So to make things simple, we know we will apply a concept of relative motion here. So we need to find the acceleration of the coin with respect to this elevator, right? So what is acceleration of coin with respect to ground? It is g, which is 9.8 meter per second square, which is basically 32 feet in feet per second square, right? We need to find what is acceleration of the coin with respect to elevator when the acceleration of elevator is a downwards, right? So simply we saw in last lecture also, to find relative quantities, let's stop the other quantity by applying an opposite vector, right? We need to find the acceleration of coin with respect to the elevator, so we will stop this elevator by applying an opposite vector, right? So let's apply opposite vector to this elevator, which is a meter per second square on the top, right? Same I'll do for the coin as well. So coin has acceleration a on the top and g on the bottom, which is gravity. So net acceleration, if you see at the coin, since it is coming downwards, so acceleration of coin with respect to elevator, this is basically g minus a meter per second square. Ignore the unit, maybe let's take this as feet per second square because distance is in feet. So acceleration of coin with respect to elevator is how much? G minus a. And this is the effective acceleration of the coin. Now using this acceleration, now I'll be able to relate all the quantities. Let's see how. So you know, by equation of motion, s equal to ut plus half at square, right? S equal to ut plus half at square. Initial velocity is 0, this ut term will go off. S I know, S is nothing but d, distance. So 6 equal to half into a becomes g minus a, and this becomes 1 square, right? So this becomes half into 32 minus a, since it is in feet, into 6. 32 minus a equal to 12, and acceleration is 20 meter per second square. So the elevator is coming down with an acceleration of 20 meter per second square. So next topic for us is Rain Man problem, right? Before going to the topic, let's understand this is a problem of relative motion in two dimension. And this problem basically talks about how a man's velocity when interacted with the falling rain, how things change, like how observation of man changes, how he assumes to see that the rain is falling at a different angle. Initially when he becomes at rest, rain may fall vertically, rain may fall at a fixed angle, but when he takes some velocity, he starts running or things like that, he will observe that the rain is actually falling from a different angle, and to calculate that angle we need to have this relative motion concept, right? So let's say initially whenever we specify any velocity and we don't mention any reference or frame, this is basically in the ground frame, right? So initially, let's for an example, let's say that before going into man problem, let's understand that if a and b are two bodies, right? A and b are two bodies. So velocity of A with respect to velocity of B is indicated by A comma B, and this is given by VA minus VB, right? VA minus VB. So let's say if VA is this vectorically and VB is this, so if I need to calculate VA with respect to B, I need to take minus of VB, which will be this one, and then I need to take the resultant, which is VA comma B, right? So this is like the law of vector addition. So this is just a recap of that. So don't forget that one. Right, now let's understand this Rainman problem a bit, right? So let's say there is a man standing, right? There is a man standing, and rain is falling vertically, right, with a velocity of VR. Rain is falling vertically with a velocity of VR. This VR is the velocity of rain with respect to ground, right? And in this case, this can also be the velocity of rain with respect to man, because man is also stationary, same as ground. So in that case, to prevent himself from a rain, he needs to hold the umbrella in the vertical direction, exactly 90 degree to the surface, right? Now, let's assume that for an instance, let's assume that with respect to horizontal, this is horizontal. Let's say that this rain is now coming at some angle. This is theta. So this rain is now coming at some angle, and the man is stationary, right? So he needs to hold his umbrella with an angle theta with respect to vertical, right? Then only he can prevent himself exactly at theta. Now what happens? He starts moving. Let's say in this direction. He starts moving in the forward direction, right? So this is VR is the velocity of rain with respect to ground. He starts moving with the velocity, let's say Vm, which is velocity of man with respect to ground again, right? So if vectorically you see, Vm is velocity of man with respect to ground, which is in the forward or plus x direction. Let's make this xy, right? And Vr, which is velocity of rain with respect to ground, right? So now, what is the observation of this man? To find observation of this man, so initially when he was at rest, he was observing that rain was coming exactly at an angle theta, right? Exactly at an angle theta. So initially when man was at rest, he was seeing that the droplets are falling at an angle theta, from an angle theta with respect to vertical, right? So here he had to hold his umbrella at the same angle, right? Now since he has started moving in forward direction, the droplets will start appearing in a different angle, right? Because since he has also acquired motion, the velocity of rain with respect to the man has changed now. So this is not the velocity of rain with respect to man. This is velocity of rain with respect to ground, which is VR. But velocity of rain with respect to man is the velocity of interest for the man. and this that is the same velocity by which that man will see, and that raindrops will appear to that man falling at that magnitude and the angle, right? So to calculate velocity of rain with respect to man, you know that it is nothing but vr minus vm, right? Relatively, if you see, v velocity of rain with respect to man is vr minus vm. This vr is nothing but vrg and vmg, right? So this is subtraction of these two vectors. So to find the subtraction, this is minus vm, and resultant of this vrg and minus vm, let's say it comes somewhere over here. So this velocity is velocity of rain with respect to man, right? This velocity is velocity of rain with respect to man, and this is the same velocity by which the rains will start to appear for this man when he has acquired motion with this velocity vm. And this, with, let's say some angle is there, so with this angle only he has to held his umbrella to save himself from the rain, right? So let's take the inferences we have from this diagram, right? So when velocity of man was zero, when velocity of man was zero, we had velocity of rain with respect to man was equal to velocity of rain with respect to ground, right? Because ground and man both were in stationary, and this vector was exactly equal to this vector, means they are overlapping to each other, right? But as this quantity starts increasing, this quantity vm starts increasing, right? So this initially, when vm was 0, this was here, velocity of rain with respect to man, this was here. But when the man has acquired velocity, the man is in motion, this vector, being the resultant of, or the negation of these two vectors, difference of these two vectors, will start projecting itself, and based on velocity of vm, it will start rotating in all this direction, right? So all these instances are there. So there will be one instance where velocity of rain with respect to man will be exactly perpendicular to the surface, and then he will have to hold his umbrella 0 degree to vertical and 90 degree to horizontal, right? So with this, I'm just trying to make you understand how the direction of rain is kind of appearing differently to a man who's in motion because of this concept, right? When he was at rest, he was seeing the rain exactly at same velocity, which is the velocity from the ground reference. But once he has acquired motion, once he has got velocity, rain is coming with respect to a different angle, and to save himself from getting wet, himself or herself, he will have to hold his umbrella with respect to vertical or horizontal, exactly at that particular angle from which the rain is appearing to come, right? So let's solve a problem on rain man problem, right? So the problem states that a man standing on road has to hold his umbrella at 30 degree with respect to vertical to keep rain away. So do remember, the man is stationary and rain is appearing to fall at 30 degree with respect to vertical, right? So let's say this is kind of a road, this is a man, and this is vertical direction, and rain is coming like this. So rain is coming to be appear from 30 degree, right? This is the diagram, and this, he is stationary as of now. So at stationary condition, you can say that the velocity of rain with respect to man is exactly the velocity of rain with respect to ground, which may be some value, right? I don't know the value. So this is velocity of rain with respect to ground, right? Velocity of rain with respect to ground. And I can also write when Vm is 0, right? When Vm is 0. So when man is stationary, the rain is falling at 30 degree with respect to vertical, and he's holding umbrella exactly at 30 degree to prevent himself from the rain. Now what happens? He now starts running at 10 kmph, right? The man starts running at 10 kmph, and he finds the drops are hitting vertically, right? So let's say when he was stationary, he was holding his umbrella at an angle 30 degree, tilted at some angle, right? But once he starts moving forward, he sees that the drops are coming vertically, and he has to hold the umbrella vertically now, right? So now I can say that the rain is now appearing to come exactly vertically with respect to the man, right? So if I draw the vector diagram of this, so this is exactly which is 30 degree with this is velocity of rain with respect to ground, which is this is velocity of rain with respect to ground, right? Which is inclined at 30 degree to the vertical. Now let's say man starts moving in this direction. This is velocity of man with respect to ground. If nothing is given, the velocity is with respect to ground. This quantity is given to us, which is 10 kmph, kilometer per hour, right? Now after he starts running, he says that the rain is appearing vertically. So velocity of rain with respect to man is vertical now. So this exactly at this angle, 90 degree. So this is velocity of rain with respect to man, right? This is velocity of rain with respect to man, and this is exactly overlapping with the horizontal, right? Overlapping with the horizontal, right? Now we need to find velocity of rain with respect to road or ground and velocity of rain with respect to man. So these two quantities, velocity of rain with respect to man and velocity of rain with respect to ground. And what we know the velocity of moving man with respect to ground, right? So it's not that we just know this thing, we know more things here. So do note that when he was stationary, the droplets were coming exactly at 30 degree and he was holding his umbrella in this 30 degree, right? Now he has started running in forward direction with 10 kmph and raindrops are coming vertically to him and he has to hold his umbrella exactly in this manner, right? So now we can solve this problem very easily using vector method. You can see that if I take ratio here, right? If I take ratio, I can say that this VRG cos theta is VRM. Like if I resolve this vector, this is a resultant vector of these two. You can easily say that this VRG is resultant of VRM and VMG. How? You see, VRM plus VMG, right? If I take this is VR minus VM and this is VM minus VG, VM will cancel. This is VR minus VG, which is velocity of rain with respect to ground. So velocity of rain with respect to ground is resultant of velocity of rain with respect to man and velocity of man with respect to ground, right? Now I can say that VRG sine theta component is nothing but VMG, which is 10. So I can say that VRG is 10 into 2, which is 20 kilometer per hour. And similarly, I can take the cos theta component and that becomes velocity of rain with respect to man. And I'm able to find all the quantities which is needed for this question, right? So let's solve one more problem on this topic. So the problem states that a man running on a horizontal road at 8 km per hour, he finds the rain falling vertically, right? So do mind that the rain is appearing to fall vertically to him when he is moving at 8 km per hour, right? And now he increases his speed to 12 km per hour and finds that rain makes angle 30 degree with respect to vertical. So we need to find the speed and direction of rain, right? Okay. Let's draw two different diagrams for these two different cases, right? So if I separate these two, right? So when velocity of man with respect to ground was 8, the rain was coming exactly vertically to him. So velocity of rain with respect to man will be exactly at 90 degree to that point, right? And where will velocity of rain with respect to ground will come here? This will be the sum of these two vectors. So this will be somewhere like velocity of rain with respect to ground. And let's say that it makes some angle alpha with respect to the vertical, right? It makes some angle with alpha with respect to vertical. Now what happens? This VMG, right? This VMG, the man has increased his speed, right? And now the new speed has become a sorry Vm comma G has become 12 kilometer per hour, right? And at this speed he is seeing that rain is hitting him with 30 degree with respect to vertical. So if this is vertical, rain is hitting him 30 degree with respect to vertical, right? And since speed has increased, we have taken the shift in the clockwise direction. You see, this is rain with respect to man, which is exactly vertical. Now we have taken 30-degree, which is in the positive or clockwise direction, not in the opposite direction, because speed has increased and the deflection will increase in the opposite direction, right? So now you can say that this rain is hitting him at 30 degrees, right? And now we need to find what is the speed and direction of rain. Only thing which is constant in both the cases is the velocity of rain with respect to ground. So velocity of rain with respect to a stationary ground, with respect to a road, will never change. So velocity of rain with respect to ground here also will be exactly like this and will be tilted alpha with respect to vertical. And we need to find this alpha and this value, right? So now with some vector smartness you will be able to appreciate and calculate these values, right? So now tell me, velocity of rain with respect to ground, sine alpha will be what? 8 in this case. Simple, it will be 8. But here there is no direct case. We need to find some orthogonal components before applying some sort of rule here, right? We need to find something here, right? Okay, let's say there is a vector here, right? Let's say there is a vector here which is orthogonal to VRM, orthogonal to VRM. So this is 90, this will become 30. Overall, this is 90 plus 30, 120. And since this is orthogonal to this VRM, this is 90 and this becomes 30, right? So component of this VMG on this will be what? VMG cos 30, right? Now I can apply and I can resolve the vectors because now I have got two perpendicular vectors like this case here also. Now I can say that velocity of rain with respect to ground sine of 30 plus alpha equal to this VMG is 12, 12 cos 30, 12 cos 30. This is equation 2, right? Now let's take the ratio 2 by 1. Remove this partition now. 2 by 1, right? So sine 30 plus alpha by sine alpha equal to 12 into root 3 by 2 into 8. And if I calculate this, this is 3 root 3 by 8, right? Now using different laws of trigonometry, you will be able to find what is the value of alpha here, right? What is the value of alpha? So let's calculate what is the alpha here. Let's take fresh this expression and calculate what is alpha. So we found that sine 30 plus alpha by sine alpha is, what was that? 12 cos 30 by 8, which is 12 into root 3 by 2 into 8. This was the value, right? And this was something like 3 root 3 by 4, right? This was 3 root 3 by 4. Now let's break this. This becomes what? Sine 30 cos alpha plus cos 30 sine alpha by sine alpha is 3 root 3 by 4. This is what? 3 root 3 by 4, right? Now take the ratio. This is sine 30 cot alpha, this is cos 30, and this is nothing but 3 root 3 by 4. So this becomes 1 by 2 cot alpha equal to 3 root 3 by 4 minus root 3 by 2. And if I take this out, this becomes 3 by 2 minus 1, and this becomes root 3 by 2 into 1 by 2, and cot alpha becomes root 3 by 2, and alpha becomes cot inverse root 3 by 2. Alpha becomes cot inverse root 3 by 2. And putting this alpha here, you will be able to find what is the value of PRG, right? So now we know the velocity of rain with respect to ground and also the angle rain is making with respect to vertical, right, in the stationary case. So we'll discuss more problems on this topic, Rainman problem and even the river boat problem in the next session. And after that, we'll move to the next unit, which are laws of motion, right? Thanks.